The objective of this lecture is to provide the second part of the discussion of the orbit in space. This lecture focuses on the determination of orbital elements from position and velocity. This lecture will be divided into the following parts. First, we will provide an overall structure for computing orbital elements. And then, using that structure, we will develop a method for computing orbital elements. Given position and velocity. And in particular, we're going to be given position and inertial velocity expressed in Earth-centered inertial coordinates, or planet-centered inertial coordinates, but we're dealing with mostly the Earth, so Earth-centered inertial coordinates. And the algorithm, or the method that we develop, is going to include computations of the following quantities. So compute the quantities, which are the semi-major axis, the eccentricity, the longitude of the ascending node, and then the orbital inclination, the argument of the periapsis, and finally, the true anomaly. Now, what's going to be really important in this lecture is that, and this is the starting point, is that the starting point is that we are given position and inertial velocity expressed in Earth-centered inertial coordinates. And these are Earth-centered inertial Cartesian coordinates. So that's the starting point for the discussion that follows. So let's first provide the overall structure. For computing orbital elements. So here's what this looks like. So recall the 6 orbital elements. And of course, these are also referred to as the 6 classical orbital elements. And they are A, which is the semi-major axis, E, which is the eccentricity, omega, which is the longitude of the ascending node, and then I, which is the orbital inclination, and then omega, little omega, which is the argument of the periapsis. And then nu, which is the true anomaly. Now, the importance of these different orbital elements are A and E together provide the size and shape of the orbit. And in fact, the value of E itself tells you what kind of orbit it is, whether it's an ellipse, a parabola, or a hyperbola. The three angles, omega, I, and little omega, together provide the orientation of the orbit relative to the basis Ix, Iy, Iz, where that basis Ix, Iy, Iz is the ECI basis, or the Earth-centered inertial basis. And then finally, the last quantity, nu, tells us the location of the spacecraft on the orbit. So now what we're going to do is we're going to actually draw a few pictures, and we're going to get the structure clarified further. So let's start with a three-dimensional view. So in this three-dimensional view, we have the basis Ix, Iy, Iz. We have this point O, which is the location of the central body. And then we have the orbit. Now, I'm going to draw this as an ellipse, but of course it could be any orbit. But arbitrarily, I'm just going to say it's an ellipse. Now, there's the closest point on this ellipse, which is the periapsis. So that point is going to be labeled P. And that direction from O to P, what lies along it is the eccentricity. If I go in the exact opposite direction, the point that's furthest away on the orbit is the apoapsis. So P is the periapsis, and A is the apoapsis. And the spacecraft is located somewhere on this orbit. So here's the spacecraft, that's S. And then the angle between E and the position of the spacecraft, which is R, is nu. But we need more than that. We need all these other orbital elements. So remember that the direction, which is normal to the eccentricity and also normal to the orbit plane, is the specific angular momentum. And then if I take Iz crossed with H, as I described in the previous lecture, that gives us what's called the line of nodes. And the angle between Ix and the vector n, that angle is the longitude of the ascending node. And the inclination is the angle between Iz and H, and then the argument of the periapsis is the angle between N and E. Now what's missing from this diagram is what you can see in 2 dimensions with a 2-dimensional view. So let's look at a 2-dimensional view. So in a 2-dimensional view, we can actually see the semi-major axis and the eccentricity. So here's the ellipse in a 2-dimensional view. And remember that the points that are important here is we have the focus O, and we have the periapsis P, and then we have this other vacant focus, which is this point O prime, and then we have the center of the ellipse. And if we draw the center of the ellipse is sort of vertically this way, this distance from the center to O is A times E, as it is from C to O prime. That's also A times E. And this distance to the periapsis from O is RP, and the distance from O all the way out to the apoapsis, which is here, that distance is RA. And then we have the semi-major axis and the semi-minor axis, but we can see that we have both the semi-major axis and the eccentricity on this diagram. So now we have all of the orbital elements in one of these two diagrams. So now we're going to actually figure out how to compute the orbital elements. So computing orbital elements from position and inertial velocity. Now, it's important to know again, we're given R and VI expressed in I, which is equal to Ix, Iy, Iz. But we're also given the gravitational parameter. Because if we don't know the gravitational parameter, we don't know anything about the planet. And so we have to be given the gravitational parameter mu. So that's important. And we want A, E, omega, I, little omega, and nu. Those are the 6 quantities we want. So let's start. So first, we can compute HI. As HI is equal to R crossed with VI. And of course, we can compute that because we're given R and VI, right? So now what we can do is we can also get the magnitude of the position, which is the radius. So R is equal to the magnitude of R, of the position R. So from that, we can actually compute the eccentricity vector, which is going to be VI crossed with HI, all divided by mu, minus R divided by the magnitude of R, which is equal to VI crossed with HI, all divided by mu, minus R divided by the radius. Now, once we have the eccentricity vector, we can get the eccentricity, which is just the magnitude of the eccentricity vector. So there's one of the orbital elements. It's not the semi-major axis, which is, of course, the first orbital element in this list, but it's one of the 6 orbital elements. Now, once we have the eccentricity, we can actually get the semi-major axis, which we'll do next. So next, we know that given HI, we can compute the magnitude of HI, which is just H, and from that we can actually compute the parameter, which is equal to H squared over mu, because again we're given mu, right? So we know what mu is, so as a result we can compute H squared over mu. Once we have that, we can actually compute the semi-major axis, which is equal to P over 1 minus E squared, because we have E. So that gives us the second orbital element. So now A and E are both computed from R and V. The harder parts are now going to be to determine the three angles, the three Euler angles, and then the fourth angle, which is the true anomaly. So next we want to compute omega. So let's figure out how to get omega. So we know that the direction that we're interested in, because if we look at the diagram, this direction is Ix, this direction is Iy, and this direction, when I'm done computing Iz crossed with h, that's actually n, and this direction, which is the unit vector along that, is nx, and this angle here is omega. So now we can actually compute the tangent of omega from this. So we know the tangent of omega is equal to, well, nx is a unit vector, so it's nx dotted with iy, that's the sine component, and then nx dotted with ix, that's the cosine component. But nx is equal to n divided by its magnitude. So let's say let little n equal the magnitude of the line of nodes. So that's equal to n divided by n. And so from that, we can actually substitute in to get the tangent of omega. So therefore, the tangent of omega is equal to, well, it's nx dotted with iy, all divided by nx dotted with ix, which is equal to n divided by its magnitude dotted with iy, all divided by n divided by its magnitude again dotted with ix. So if I multiply through by n, the magnitude of the line of nodes, I get that the tangent of omega is equal to n dotted with iy, all divided by n dotted with ix. Now that gives us the tangent, but we actually want omega. So what we're going to do is we're going to actually take the inverse tangent, and we're going to take the inverse tangent using what's called a four-quadrant inverse tangent. So omega is going to equal the inverse tangent of n dotted with iy, n dotted with ix. This is what's called a four-quadrant inverse tangent. And it turns out that it's actually available in all computing platforms exactly in that form. It takes two arguments. It takes y and x. The first argument's y, the second argument is x. And it's actually on a computer, it's often referred to as a tan 2. And it would be a tan 2 y comma x. Now, once we have that, we actually have the angle. But the only issue with the angle is that the four-quadrant inverse tangent actually gives you an angle on negative pi to pi using the four-quadrant inverse tangent. And we actually want an angle on 0 to pi. So there's a simple fix for this, which is that if omega is less than 0, that means we're actually going to get a negative angle. What we do is we update omega and we add 2 pi to it, only in that case. So omega is less than 0, we take the value of omega and we add 2 pi to it. And that becomes our longitude of the ascending node. So now once we have the longitude of the ascending node, the next thing we need to figure out is we need to figure out the orbital inclination. So we'll do that on the next page. So to compute the orbital inclination, recall that the orbital inclination is the angle between the vector iz and the vector hi. So this angle is the orbital inclination. Now, in order to add some useful other information to the diagram, the direction out of the page is nx because it's actually along the direction n, and iz crossed with h is the direction of the line of nodes, and nx is the unit vector in that direction. And then ny is the direction off to the right, which makes negative ny the direction to the left. So from this, we can actually compute the orbital inclination. I'm going to do one other thing that may help this, but before we actually do this, let's start with the calculation because we have the vector h, right? So we know that the tangent of the inclination is equal to, well, what's the sine component and what's the cosine component? Well, the sine component is hi dotted with minus ny, because that's the side opposite the angle. And then hi dotted with iz. Remember, this is also nz. So I'm going to start by putting nz here. So this becomes minus hi dotted with ny, all divided by hi dotted with nz. And now we're going to start substituting. All right, so we know that nx is equal to n divided by its magnitude. So, and we also know that nz is equal to iz. So as a result, we can actually compute ny. ny is equal to nz crossed with nx, and that's equal to nz, which is iz, crossed with n divided by its magnitude, which is equal to iz crossed with n divided by its magnitude, where, again, I've said that n in magnitude is equal to the magnitude of the line of nodes. So from this, we can actually compute the tangent of the inclination. So the tangent of the inclination becomes, well, let's start substituting. We've got minus hi dotted with ny, but ny is iz crossed with n divided by its magnitude, all divided by the quantity hi dotted with iz. So when we're all done with this, now what I'm going to do is I'm going to do two things at once. First, I'm going to multiply the numerator and denominator through by the scalar n. The second thing is I'm going to get rid of the negative sign by flipping the order of the vector product. So I've got iz crossed with n. I'm going to make it n crossed with iz. So when I do all that, I wind up with hi dotted with n crossed with iz, and that's going to be divided by n times hi dotted with iz. So now I can take that result and I can put it on the next page to compute the orbital inclination. So we then have that the inclination is equal to the tangent inverse of, and this is the 4-quadrant inverse tangent again. So we have hi dotted with n crossed with iz in the first argument, and in the second argument we have n times hi dotted with iz. Now, although this gives a result that's on negative pi to pi, it turns out that I will actually be on 0 to pi with this calculation. So we don't need to do anything because the orbital inclination is only defined on 0 to pi. And so this result is correct. There's no modification that needs to be made to the angle at all. So with this calculation, so I'm going to write that out. It says it turns out that I is on 0 to 2 pi using the above calculation. So there's no modification needed. So the last of these three Euler angles is we need to compute the argument of periapsis. So the argument of the periapsis is computed as follows. So we know that the argument of periapsis is the angle between E and N. So here's N, and here's E. So that's the argument of the periapsis. So we know in this diagram that the direction out of the page is actually equal to the specific angular momentum. And so we're going to use that fact to be able to do the rest of this calculation, because if out of the page is the specific angular momentum and along the right direction is n, then that means that the direction that's going up in this diagram is hi crossed with n, right? So now we actually can figure out how to do the different components of the eccentricity to actually get the argument of periapsis. So we know that the tangent of the argument of periapsis has to equal, well, what it really has to equal is it's got to equal E dotted with the unit vector components along n and along h cross n, where the h cross n component is the sine component and the n component is the cosine component. So this has to equal E dotted with hi crossed with n, all divided by the magnitude of hi crossed with n, all divided by E dotted with n divided by its magnitude. And the reason it has to look that way is because I have to take the scalar product with unit vectors. I can't take the scalar product with anything else, otherwise I won't get the correct components in sine and cosine. So as a result of doing this, we know the following: that hi and n are orthogonal. So what that implies is it implies that hi crossed with n in magnitude is equal to the magnitude of hi times the magnitude of n. And I can substitute that in to the expression above, and I get that the tangent of the argument of the periapsis is then equal to E dotted with hi crossed with n, all divided by the magnitude of hi times the magnitude of n, all divided by E times n over the magnitude of n. Now I can substitute in all the things I defined before, which is magnitude of hi is h, so this gives me E dotted with hi crossed with n, all divided by hn, all divided by E dotted with n divided by the magnitude of n. So from this I actually can simplify quite a bit, and I get that the tangent of the argument of the periapsis I'm going to multiply through by hn in both the numerator and denominator, and I get E dotted with hi crossed with n, all divided by h times E dotted with n. And that's the tangent of the argument of the periapsis. So now I can use the tangent to be able to then compute the actual argument of the periapsis, which is going to be the inverse tangent of this result. So then the argument of periapsis is equal to the 4-quadrant inverse tangent of E dotted with hi crossed with n, and in the second argument, h times E dotted with n. Now again, because this is a 4-quadrant inverse tangent, we get an angle on negative pi to pi. And in this case, we actually will get an angle on negative pi to pi. So if omega is less than 0, then what we do is we add 2 pi. We say omega is changed by omega plus 2 pi. So anytime we get something that's negative, we just replace it with adding 2 pi. It's the same angle, but then it just puts everything on 0 to 2 pi instead of it being on on negative pi to pi. So that changes this to be a positive angle always. So now we're done with the argument of the periapsis. So the last thing we need to do is we need to compute the true anomaly. Well, the diagram for the true anomaly looks really similar to what it looked like for the argument of the periapsis, because the angle nu is the angle between the eccentricity vector and the position. So this is the angle nu. And again, the direction out of the page in this diagram is the specific angular momentum, which makes the vector pointing upward in this diagram hi crossed with e. And now we can go through an almost identical argument to what we did to compute the argument of the periapsis. So we then have that the tangent of the true anomaly is equal to r dotted with, well, the unit vector in the direction which forms the sine component is well, we've got h crossed with e divided by the magnitude of h crossed with e, and we're taking the dot product with r. That gives us the sine component. The cosine component is r dotted with e divided by its magnitude, which is just the eccentricity itself, right? Now again, because hi and e are orthogonal, that implies that hi crossed with e in magnitude is just equal to the magnitude of hi times the magnitude of e, which is just equal to he. So then, the tangent of the true anomaly is equal to, well, the numerator looks like r dotted with hi crossed with e, all divided by he, because I just computed he. And the denominator looks like r dotted with e divided by its magnitude. Now, if I multiply through by he, the numerator becomes r dotted with hi crossed with e, and the denominator becomes, well, the e cancels out, but I'm still left with h times r dotted with e. So as a result, the true anomaly becomes the four-quadrant inverse tangent of r dotted with hi crossed with e, and then the magnitude of hi, which is h times r dotted with e, and that again is on the interval negative pi to pi. And so we go through the same calculation that we did before, which is that if nu is less than 0, then what we do is we take nu and we replace it with nu plus 2 pi, only if it's less than 0. If it's greater than 0, we don't do anything at all, just like we didn't do with the other angles. So the calculations are now completed. We've finished all 6 orbital elements in terms of position and velocity. So that basically takes us to the end of this lecture. We have a method or an algorithm, if you want to call it that, for computing the 6 orbital elements given position and velocity. And you'll notice that all of these calculations require us to use scalar and vector products, and they all start with position and velocity. Once we do that, we just start moving through these calculations in such a way that we build on what we did before, and we get each angle of these orbital elements, and we get the semi-major axis, and we get the eccentricity, and then we get all 6 orbital elements as a result. So using the aforementioned derivation, we can now develop a procedure for computing orbital elements from position and velocity. Now, this procedure is essentially a restatement of everything we just did, but it provides everything in one place so that it's possible to go through steps. You can think of it almost like an algorithm to be able to compute the orbital elements. So we're given the following information: the position, the inertial velocity, and we're given the gravitational parameter mu. And remember that the position and velocity are expressed in Earth-centered inertial coordinates or planet-centered inertial coordinates. So now, given that information, here's the process. So, computation of the orbital elements. So first, we compute the specific angular momentum, which is HI, which is equal to R crossed with VI. Once we have that, we can compute the magnitude of the specific angular momentum because we need it for later on. Once we have that, we can compute the radius, which is equal to the magnitude of the position. Now, this information can then be used to construct or compute the eccentricity vector. So the eccentricity vector is equal to VI crossed with HI, all divided by mu, minus R divided by its magnitude. Once we have the eccentricity vector, we can compute the eccentricity, which is equal to the magnitude of the eccentricity vector. Next, we can actually compute the parameter, which is equal to h squared all divided by mu. Now notice that we have the magnitude of the specific angular momentum because we computed it earlier. So from that, we can actually get the semi-major axis, and that's going to equal p all divided by 1 minus e squared. Now you'll see that e, well, that's one of the orbital elements. This is actually the second orbital element, and this one's actually the first orbital element. So even though the order is A and E, we actually get E first before we get A. But the ordering of the orbital elements is AE. Then, once we actually have these two orbital elements, we can compute the four angles. So the four angles can be computed as follows. First, we need the line of nodes, which we recall is equal to IZ crossed with HI. Once we have the line of nodes, we can compute the magnitude of the line of nodes, which is just denoted with a scalar n. And then we can go ahead and compute the four angles. So the first of these angles is the longitude of the ascending node. And the longitude of the ascending node is equal to the four-quadrant inverse tangent of n dotted with IY and n dotted with IX. Now this gives us an angle that's on negative pi to plus pi. But we actually want an angle that's on 0 to 2 pi. So if it turns out that the longitude of the ascending node is less than 0, it gets replaced with itself plus 2 pi. And this gives us the third orbital element, because this angle is actually now on 0 to 2 pi, which is the convention that we want to use. The next angle is the orbital inclination. Now the orbital inclination is equal to the four-quadrant inverse tangent of HI dotted with n crossed with IZ, and then scalar n, which is the magnitude of n, times HI dotted with IZ. Now it's important, again, to understand that this angle is already on the correct interval. It's on 0 to pi, so we don't have to adjust it. This one gives us the fourth orbital element, which is the orbital inclination. The next orbital element is the argument of the periapsis, which is equal to the four-quadrant inverse tangent of E dotted with HI crossed with N, and the magnitude of HI, which is H, times E dotted with N. Now this angle is again on negative pi to pi. So we can replace the angle if it's less than 0. We replace it with itself plus 2 pi, and that gives us an angle that's on 0 to 2 pi. And this is now the 5th orbital element. The 6th orbital element is nu, which is the true anomaly, which is the 4-quadrant inverse tangent of r dotted with hi crossed with e, and the magnitude of h times r dotted with e. This angle again is on negative pi to pi, so if it turns out that the angle is less than 0, we replace it with itself plus 2 pi, and these calculations together give us the 6th orbital element. So we now have A, E, omega, little I, little omega, and nu from the above sequence of calculations. So the aforementioned sequence of calculations provides for us a method for determining the orbital elements given the position, the inertial velocity, and the gravitational parameter. Once we have those 3 pieces of information, this sequence of calculations can be used in the order in which I have written it in order to be able to compute all 6 orbital elements. So that takes us to the end of this particular lecture. So to summarize what we did in this lecture, the first thing we did is we provided an overall structure for computing orbital elements. And using that structure, we actually developed a method for computing or for determining orbital elements given position and velocity. And of course, it's the inertial velocity. And that gave us a way of being able to compute the semi-major axis, the eccentricity, the longitude of the ascending node, the orbital inclination, the argument of the periapsis, and finally, the true anomaly. And this method is going to form the basis for being able to do calculations, to be able to understand orbits, and to be able to analyze orbits. And we'll be using it in the future with this material.